In this video, which is the second part of 13A, we're going to look at displaying sample spaces, and then we're going to look at how you determine probabilities from those particular sample displays. So we're going to look at Venn diagrams, we're going to look at probability tables, and we're going to look at tree diagrams. We're going to look at how the Venn diagram and the probability table are related, and we're going to look at tree diagrams and how you use them when you have different probabilities and the same probabilities on each branch, and how they actually work. So let's start with Venn diagrams. So our Venn diagrams have a rectangle with the sample space symbol, the universal set symbol up here, and each set of values within, or each event within our sample space has a circle and its letter attached to it. The bit in the middle we call the intersection, and it has this little N-shaped little lump. Okay, it's not the letter N, it's a little lump. And we also have the union of A and B, which is a little U. And from the Venn diagram, we can see that if we wanted to find the union of A and B, we can do that using our probabilities for A and probabilities for B, and the probability of the intersection in between. And to do that, we use what's called the addition law of probability. And you can see that the union of A and B, which is the whole section contained within those two circles, is equal to the pink section, the total of the pink section, plus the total of the blue section, take away one of the purple section, which is in the middle here, because you can see that it's counted in the pink and it's counted in the blue. And so what you've got here is almost like you've got a little intersection, let's call it N and N, and so you want to get rid of one of those N's, so you just take one of those N's away. So this formula here is on your formula sheet for both exams, and it is something that you need to be able to use and remember. It also helps us when we're trying to recognise mutually exclusive events. And mutually exclusive events, remember, they are the ones where if one happens, it excludes the other from happening. Mutually exclusive events on a Venn diagram appear as two separate circles, and so the intersection between the two is equal to 0, which means that our law of probability formula up here now has a -0 for the probability of A minus B. So you get just the probability of A union B is equal to the probability of A plus the probability of B. Now, it is common that they expect you to remember the fact that if two events are mutually exclusive, that implies that the intersection between the two is 0. And you'll see that multiple times when you're doing practice exam questions, that they assume that you remember that. So make sure that you put that into your notes book. So the next useful way to display your sample space is using a probability table. And a probability table is this thing here. And it reflects directly the sections that you have in your Venn diagram. And you can see I've color-coded the corresponding sections in the Venn diagram and in the probability table. And so if we go through and we talk about what the actual definition of these particular sections are, I'll fill them in over here for you. So we look at, for this particular cell here, for this particular position in the table, it's the intersection of the column header and the row header. So it's the intersection of the column and the row, and so it is in fact A intersect B or B intersect A. Same deal. And it's the yellow section of the Venn diagram. The next bit coming across is also B. This time it's intersecting with A naught, and so it's the green section of the Venn diagram, and the same with the others. And so what do these little extra sections in the probability table actually record? Well, what they record is the total of this column for A. So the total for the column for A is the probability of A. The total for the probability of A naught is the probability, the total for the probability of A naught column is the probability of A naught. And the same with the rows. This will be the probability of B, and this will be the probability of B naught. The other thing that we need to talk about is this 1 down in the bottom corner of the probability table, and it's there for a particular reason. And what it is that the total probability that's contained within this whole table here is going to equal to 1. And we can check this out using the rows and the columns. So every row sums to the answer on the end, and every column sums to the answer below. And this allows us to find missing probabilities quite quickly. Let's have a look. So we're going to have a go at two different probability tables, and these are the pieces of information that were given for the first one. So probability of A intersect B is 0.3, so that goes in here. Probability of A naught intersect B naught, so B naught intersect A naught, so that goes in here. And probability of A is 0.6, so that goes in here. So now we go through the process of filling in the other values, knowing that the rows are going to add, these two are going to add to give us 0.6, which means that this number in here is 0.3. And then what we're looking for is where can we fill in the rows and the columns. So the next thing that we've got these two values here. They should add together to the value in here, which means that that is 0.5. Next we look for another row or column that has a missing value and fill that in. So we'll fill in 0.4 here, 0.5 here. Since that row has to add to 1 and that column has to add to 1, and then finally we just need to make this spot fit both this way and this way, which puts 0.2 in that position. Let's have a go with the fractions one. My suggestion is that you pause, you put it in, try and fill in the rest, and then check with my answers. Away you go. How did you go? Tree diagrams are useful when you've got more than two events happening that you're interested in, and each split on the tree represents a new chance situation. So each split, this is what I mean down here, where the two lines separate. So each split here is a new chance situation. And each branch of the tree, so a branch of the tree is from the start all the way to the end, so you can see we've got lots of branches here, is a possible sequence of events. So for example, we've got a fair coin that's flipped 3 times. So on our first flip we have a chance situation, so it splits and it can be either heads or tails. And then whether it's heads or whether it's tails, we then do our second flip. And if it's heads on the first flip, the next chance situation is that on the second flip it'll be heads or it will be tails. If it's tails on the first flip, you still have a chance situation from there that it will be heads or tails. And so each of these lists or columns of outcomes represent a new chance situation, the first flip, the second flip, and the third flip. So we follow along the branches to make our outcomes. These are all our possible outcomes here. And we can work out the probabilities of those outcomes if all of these splits are equally likely. So this is a 50-50 split. That means that each one of these particular outcomes is also equally likely. And we know with probabilities that the probabilities should total to 1. And so we've got 8 of the same things. 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 outcomes that are all equally likely. So each one of those outcomes has a probability of 1/8. 1/8. 1/8. Etc., etc., etc. Each one of these is 1/8. If we have a situation where a coin is not a fair coin, so each side doesn't have the same chance of being chosen, then what we get is a tree with different probabilities for each split. And so you can see here I've got on the first flip, probability that it will be heads is 0.6 and the probability that it will be tails is 0.4. So again, on our second flip, if we're using the same coin, our probabilities will be 0.6 and 0.4. And also for the next branch below, if it lands tails on the first flip, it's still 0.6 for heads and 0.4 for tails. And we do that for the rest of the branches. So we know with the probabilities that the probability of all of those possible outcomes will all add to 1. To work out the probability of each individual outcome, what we do is we multiply the probabilities as we go along each branch. And that is the same for every one of the outcomes. You multiply along the branch to give you your probability. Now, you can see for these probabilities here that I have simplified them using powers. We'll make use of these when we look at discrete random variables and bivariate variables, but this just makes it easier to see that what you're getting is multiple versions of the same outcome that have the same probability. So that's how you do a tree diagram if they're not equally likely outcomes, but the outcomes remain the same for each different trial. So what happens if, as you move from one chance experiment to the next chance experiment, if the probabilities actually change? And that situation happens when you make a selection from something without replacement. So let's have a look at those. Selection without replacement. So a chocolate box contains 2 mints and 3 caramel chocolates. 3 chocolates are selected at random from the box without replacement. So choice number 1 from the box will be either a mint or a caramel. Choice number 2 will be either a mint or a caramel, regardless of what happened in choice number 1. But choice number 3 will be a little bit different. But first, let's put the probabilities on for each of these different choices. So the very first time you make a choice, you've got 2 mints and 3 caramels in the box. And so the chance of selecting a mint is 2 out of 5, and the chance of selecting a caramel is 3 out of 5. So always with a tree diagram, these 2 branches will add to 1. So in our second choice, what we've got now is a box for this particular branch. We've got one of the mints taken out, which means when we come to choosing our second choice here, we are now choosing out of just a total of 4. So each of our probabilities will now be out of 4 because one chocolate has already been chosen. Now left in the box, if we've chosen one mint, is one mint left, which means the probability of selecting that mint will be 1 out of 4. The probability of selecting a caramel, there's 3 of those left, will be 3 out of 4. If, however, on our first choice, we choose a caramel, that means that we still have 2 mints and 2 caramels left. So the chance of choosing a mint is 2 out of 4, and the chance of choosing a caramel is also 2 out of 4. So now it's time for our third choice, and our third choice is going to be with just 3 total chocolates left in the box, because we've already taken out 1 chocolate each in our first 2 choices. So now we have to think about, if our first choice is a mint and our second choice is also a mint, then the only thing that's left in the box is a caramel. And so the probability from 3 caramels of choosing a caramel is 3 out of 3, or 1. On the second branch down, if we've chosen a mint on our first one and a caramel on our second one, we have both mint and caramel to choose from. So there is still 1 mint left out of the 3 chocolates that are left, and there are 2 caramels left out of the 3 chocolates that are left. We'll do the same with that if we chose a caramel first and then we chose a mint. We would have both caramel and mint left in the box. So we have a split here, a mint and a caramel. And in the box, the chance of choosing a mint, there's 3 chocolates left, remember. One of the mints is already gone, which means that the chance of choosing the other mint is 1 out of 3, and the chance of choosing a caramel is 2 out of 3. And then finally, if our first choice is a caramel and our second choice is a caramel, we still have mint and caramel available for selection in that last choice. A mint and a caramel. And this time there is only 1 caramel left, so 1 out of the 3 for caramel, and there are 2 mints left, so it will be 2 out of 3 for the mint. So when you're doing selection without replacement, you need to think really carefully about the fact that the total number of things that you're choosing from goes down with each choice. So we had 5 items to choose from at the start. Then our second choice we had 4 to choose from, and our third choice we had 3 to choose from. And depending on what had already come out, our third choice was different for different previous outcomes. So you need to be careful and watch for those things. So to work out the probabilities, you use exactly the same process, work out what your outcomes are, and then multiply along the branches to make each probability. At the end, the probabilities should all sum to 1. If you wanted to then use that tree to find something like what is the probability that 2 mints were chosen, what you need to do is to go through and select all of the possible outcomes that contain 2 mints. So we have 2 mints here and here and here, and for each of those outcomes we add their probabilities together. So the probability that 2 mints were chosen was 6 out of 60, and we've got that 3 times. We add them together. So that's going to give us 18 out of 60, which we can simplify down to be 3 out of 20.